Thank you very much for introduction. Good afternoon, everybody. My name is Sergiy Korposh, and I'm a associate professor at the University of Nottingham, and I would like to present today our work on crystallization of optical fiber sensors with metal organic frameworks to detect ethanol vapor. Before I go to my research presentation, just a brief introduction of the University of Nottingham. It's one of the largest universities in UK with around 35,000 students. We have three campuses, one in UK, in Nottingham, one in China, and one in Malaysia. I belong to Optics and Photonics group, or former Applied Optics group, and this is one of the largest group in engineering faculty. We position ourselves, our research, to take from fundamentals, developing sensing technology, and bringing it to application. So where we're located, so Nottingham is located in Midlands, about 100 kilometers north from London. And in Nottingham, our department is located very close to Queen's Medical Centre, which is one of the largest European education and research hospitals. So this drives a lot of our work. So we are developing optical fiber sensors for healthcare applications. If you have a chance to visit Nottingham, I strongly recommend. It's one of the highlights of the project. They have one of the oldest pubs, or they claim oldest pub in UK. Just dated back to 1189, and of course Nottingham is famous for legends of Robin Hood. Okay, turning to research presentation. So this outline, I will very briefly give an introduction to optical fiber sensors, what sensing platform we're using, then move to explain how we functionalize, what metal organic frameworks are, how we deposit them onto optical fibers, and I'll show some response to ethanol before concluding my talk. So optical fibers, they're used for telecommunication mainly. So their main application is in telecommunication. Light is guided inside the silica rod by total internal reflection. They're designed in such a way that they can transport information with very low losses to very long distances. There is influence of external environment on light that propagates inside the optical fiber, and this creates a prospect for sensor development. Of course, in telecommunications, this is something unwanted effect, but for sensor design is exactly what we want to have. Attributes of optical fibers, so they're lightweight, they have a very small dimension of 125 micrometers, a standard silica, single-mode silica optical fiber, so it's a thickness of human hair. They're immune to electromagnetic interference. They can be easily surface mounted, embedded into various structures. You can easily multiplex these optical fiber sensors, and I will talk about it as well during my presentation. They're chemically inert substrate, so as a sensor, it's very beneficial to have this property where they're not, for instance, they're not influenced by humidity. With various types of sensors, there is also effect of temperature on properties of the sensors, and I'll discuss it later on. And they're safe to use in hazardous environments because there is no electric charge, in optical fibers. So how we can make sensors? There are different ways of how to make light leaking from optical fiber interacting with surrounding environment. And easiest way probably will be to one of the easiest ways is to just take the optical fiber. So you heat this section and pull two ends of the fiber into opposite directions. So you create this thin region where light starts to leak outside, interact with surrounding medium. You can remove, also a very simple method, just remove a cladding from the core of optical fiber, and then light starts to, again, you destroy total internal reflection there, so lights will start to leak outside, interact with surrounding medium, and propagation properties inside the optical fiber will be influenced by parameters you want to measure. You can create a simple reflectometer here, where intensity of the light reflected at the tip of optical fiber will depend on refractive index of a medium it interacts with. All of these sensors are intensity based, so there is a bit of a disadvantage. You need to use a reference sum for all of this, because if your light source intensity changes, you need to be able to make sure that your change is because of a measure intervals and because of a intensity modulation of a light source. The other way of creating sensors is so-called grating sensors, and they provide wavelength encoding information. In this work, I will present long period gratings. So So what is long period grating? It's you create a periodic modulation of refractive index inside the core of optical fiber, and the typical way of doing it is you expose silica optical fiber to UV patterns, and because of the photosensitivity, it induces refractive index change where in an area where it was exposed to UV light. So you can see this pattern, this structure here. What it does to light that propagates inside the optical fiber, you couple in fundamental core mode into cladding mode. So this basically acts as a diffraction grating, and it diffracts light into cladding, and it becomes an evanescent wave at the cladding medium interface. Will interact with external medium. So what it does to transmission spectrum, if you put a broad transmission spectrum into the optical fiber that has long period grating, at the end of it you will have attenuation bands, and this position of attenuation bands depend on grating period, so the distance between two adjusting plates, effective refractive index of the core mode, and effective refractive indices of the cladding modes. So to illustrate this, so you can see that in fundamental core mode, so you have light only inside the core, no light in the cladding. If you induce this grating, if you inscribe grating inside the optical fiber, you start to couple to this modes into the cladding. So how we can make sense out of it? This attenuation band, position of this attenuation bands in transmission spectrum depends on external refractive index, basically. So the cladding mode, refractive index of cladding mode depends on external refractive index, and by changing external refractive index as illustrated here, simply for instance from air to water, you see a wavelength shift and also an amplitude decrease. So you can use this to measure refractive index. Of course, this sensor is not selectively sensitive, so any change of refractive index will lead to a change in wavelength shift here. The principle of operation, in essence, is similar to surface plasmon resonance, where you have a shift in resonance wavelength. To make them selectively sensitive, what we're doing in our work, we're functionalizing optical fibers with sensitive material that will change its optical properties in response to the presence of analyte we want to detect. So we use the selectivity. The material target we want to detect will interact with this material, we change optical properties, and we'll probe these optical properties with using optical fiber. We're using various methods to do this, so layer by layer, so we can use different methods to deposit the coat optical fibers. We use also molecular imprinting, and it's very interesting to hear the previous talk. And today I'm going to present another materials that can be used, so-called metal organic framework. So why is it good for sensing? So what is a metal organic framework? You can see in here. So you have a metal node, and you have an organic ligand around it. It has extremely high porosity, so it's, this material with the highest porosity that's not as much higher than carbon, for instance, which internal surface area is around 7,000 meters square per gram. It is equivalent to probably 2 football pitches. Application of these materials. The main application is in gas separation. So they found because of this high porosity, they're very good to store different gases. You can tailor selectivity of these materials by simply changing metal mode or organic ligand, so you can have different materials. This provides a prospect for sensor development. So we have combined these two. We combined long period gratings, optical fibers, with metal organic frameworks, and I'll just showing you the deposition results here. It was very simple. I'm not showing the scheme how this deposition was conducted, but we simply put optical fiber into solution that contain a precursor for this metal organic framework, and with the time you see assembly of this, grow of these crystals on the surface of optical fiber, because it changes optical thickness at the interface between cladding and medium. You see a change in wavelength shift, and this 1, 2, 3, 5 here corresponds to number of cycles we used to deposit. So you can deposit many layers, and again, sensitivity. It will affect sensitivity depending on number of layers. So, for instance, I'll present work today with 5 layers. This is a cross section of the metal organic framework. Advantage of optical fibers: you can measure in real time your deposition, so you can actually tell, and you can optimize the response of your sensor simply by stopping it at the right time when you have right thickness and right optical range. So, which is shown in here, for instance. So you can see in solution when the fiber is immersed into film forming solution, you can see this change, wavelength shift in attenuation band, and it because of the growing of metal grinding frameworks on the surface. So after we coated optical fiber with metal grinding frameworks, we calibrated it to expose to ethanol. In our work, we have used ethanol as solvent, and this determines the selectivity. So we have a good selectivity, so the selectivity test to ethanol, for instance, as compared to other alcohols, as methanol and propanol here, for example, and a very small sensitivity to water. Acetone does influence the sensor response, and it's mainly because selectivity is size selective, so acetone is much smaller than ethanol penetrates into these pores. Penetration of the gas into the pore will change refractive index, and we're measuring of the film, and we're measuring this refractive index. There is so as I mentioned earlier, as you can see, it's not sensitive to humidity, but there is a temperature sensitivity of this long period ratings via thermal optic effect, and also if it's high sensitivity, you'll have a elongation of optical fiber, so it will change the grating period. So position of these bands will change. In order to overcome this problem, what we can do, we can multiplex this optical fiber, so we can have two sensors with slightly different grating period, which lead to different attenuation bands present in transmission spectrum. And we can modify one grating with our sensitive layer and leave other grating unmodified, which will be sensitive only to temperature. There's no absorption side there, so no gas will influence the position of this pig here, but it is temperature sensitive, so we can measure sensitivity. So we have a response to ethanol, and we can measure temperature. So what we did with this sensor, we did a breast test. So we measured ethanol in breast, and the experiment was very simple. So we had a couple of drinks, and then measured response before and after alcohol consumption. So you can see a change in transmission spectrum here. So air, the breast without presence of alcohol, and breast with the presence of ethanol. You can see also the temperature response here. So this difference between red and blue line is that this is only effect of the temperature. By subtracting this, you can actually tell that you have a ethanol present in breast. So it's a very simple proof of concept, but we can use a different materials that will be selectively sensitive to other compounds, and in healthcare applications, this is quite convenient when you want to measure some biomarkers present in breast. So this is a preliminary focus of our work, but to demonstrate the proof of concept. So in conclusion, I've demonstrated you introduce the optical fiber long period sensors, show how we can use metal grinding frameworks to make them selectively sensitive to a particular analyte we want to detect, and also show you an example of ethanol in breast. I'd like to acknowledge all the contribution from various people in various groups and various institutions that I work with, and thank you very much for your attention.